Work done by a varying force. Yesterday we talked about work and it was the same force the whole time. Today the force is going to vary, so it's not going to be the same amount through the whole time that it's applied. So the question for today is, how do you calculate work done by a non-constant force? So that means that force value is going to vary. That's going to be different values. It's going to either get more or less as time goes on. That's in the direction of the displacement. Well, that's nice, because if the force is in the direction of the displacement, then it's always going to be cosine 0 degrees, which is 1. So we don't have to worry about the angle. So a problem you might see is, how much work is done by a force that starts at 0 newtons and increases to 2 newtons over a distance of 10 meters. So we couldn't just do work equals FD cosine theta, because F isn't the same the whole time. So we'll get back to this. We'll talk about how we actually would solve that. So let's look at an example that we did before though. So the work is FD cosine theta, and if the force is in the same direction as the displacement, then theta is 0 degrees, cosine 0 is 1. So we just get work equals FD. And if the force is 3 newtons and the displacement's 10 newtons, that's a pretty easy problem. We get the work equals 30 joules. So if we take a look at the graph of this, here's the work that we did on the last page. But here's our 3 newtons the whole time for a displacement of 10. And when we look at this, if we trace this out, the area, this shape makes out a rectangle, and the area of that rectangle is 30. And it's actually 30 joules, which was our answer here. So what we find is that if we have a graph, we can look at the area trapped between the x-axis and our graph, and that will give us the work that's done. So let's go back to that question that we had at the beginning where I said your force is going to change now. It's going to start at 0 newtons and go to 10 newtons over displacement, or to 2 newtons at a displacement of 10 meters. So that graph, it starts at 0 and it goes up here to 2 newtons over the 10 meters. And we now know that the work is equal to the area. So we get the area of this. The area of what exactly? When we get our area, the top and the bottom of the graphs always have to be the graph and the x-axis. And then we can draw a vertical line to close it off. So I have this triangle. So the area of a triangle is 1/2 base times height. So the area of this triangle is 1/2. The base is 10 and the height is 2. So that means that there was 10 joules of work done in this example. Here's one for you to try. What would be the work done by this force? So again, if we do this, remember that the work equals the area, and we can use our graph and the x-axis to do the top and the bottom. We don't need to close anything off here. So area is 1/2 base times height. The base of this triangle is 4, and the height of this triangle is 0.8. So the work done, half of 4 is 2, and 2 times 0.8 is 1.6 joules. Since we're finding the area of shapes, one shape from geometry class that would be good to know that comes up quite often in these that would make it helpful is a trapezoid. So what is a trapezoid? Remember, a trapezoid is a quadrilateral. That means it has 4 sides, 1, 2, 3, 4. And it has one set of sides that are parallel. So in this case, the top and the bottom. And the area of a trapezoid is 1/2 base 1 plus base 2 times the height. The bases are always the parallel sides, and the height is the distance between them. So here's another sample problem. How much work was done over 14 meters according to the force versus displacement graph shown below? So there's our shape, and again, we want to trace this thing out and get the area. You might try to do a shape like this, but this is not correct. And the reason why is because remember that a shape that we trace out, we can only use the graph and the x-axis for the top and the bottom. So our shape that we're going to use, actually, here's the graph, and then the x-axis comes along like this. And then we can close it off with a vertical line here. So what we have is actually a trapezoid up top. It's above the x-axis, so it's going to be positive work. And this triangle down here is below the x-axis, so it's going to be negative work. So here I'd like to just take a moment and summarize. How do you calculate the work done by a non-constant force that's in the direction of the displacement? And in this case, I'd like you to actually, practice some English skills. Write a complete statement beginning with rewriting this question. So here's another example where we could calculate how much work was done by this force. And again, what we need to do is we need to trace this thing out. Remember, use the graph itself, which will be either the top or the bottom. And then we use the x-axis. And then if we need to, we can use a vertical line to close this off. So we can close it off here with a vertical line. So this is positive work above the x-axis, negative work below the x-axis. To calculate the area here, we're going to do a couple different shapes. I'm going to use this as a trapezoid and a triangle and then a triangle. If you don't like trapezoids, then you don't have to do the trapezoids. You can always do a rectangle here and then a triangle. But I like doing a trapezoid because you can get two shapes out of one equation. So here's what the work like this would look like. Remember, here's my trapezoid. And I find that by doing my trapezoid equation. I can get the area of my trapezoid. And then here's a triangle. And I can use my 1/2 base times height and get the area of that triangle. And then I have this other triangle that dips below the x-axis, and I can do that and remember that I'm going to subtract that off, and that will result in the work done by that force. Sometimes the problem will change things up and it'll say, what is the work done from 3 to 10 meters? So we don't care about the beginning or the end, we just want to know between that. So I'm going to start off with drawing my vertical lines at 3 and 10. And then now my graph will help me being either the top or the bottom. And then the x-axis will be the other. So then I could go through and find the area of that, which is positive work, and the area of that shape, which is negative work. And finally, I'd like to just do a summary of what we talked about here. So how do you determine the work done from a non-constant force? What happens if the force is negative for part of the motion, where it goes below the x-axis? And we need two things: helpful, confusing, or questions that you might have.